So, this is the eighth lecture. I want to start by talking about the upcoming first midterm. So, the first midterm will be released at 9:30 a.m. on Friday, February 19th. It'll be due on Canvas at 9:30 a.m. on Monday, February 22nd. Between those times, you'll be permitted to communicate with other humans about the course material. There will be no further time limits or restrictions on allowed resources. So, in particular, you're encouraged to access the YouTube lectures and class notes and to communicate with artificial intelligence in the same way as you do for homework. You can also communicate with pets if you feel that would be helpful. There will be 6 questions on the midterm. There will be 2 questions on the material from each of homeworks 1 to 3. Each such pair of questions will have one green problem, which I intend to be easier, and one red problem, which I intend to be harder. I can't necessarily promise my predictions about the difficulty of problems will be accurate for everyone, but I think from what I've heard in terms of feedback, most students have agreed with my assessments of the difficulty of opposite sides of Christmas. So, I guess if you want to budget your time based on the green being easier and the red being harder, then that's reasonable. There's going to be no homework assigned on Monday, February 15th, so homework 3 is the last homework that will be assigned before the midterm. There will be an optional practice exam released on Monday, February 15th. It will have exactly the same format as the midterm. There will be no lecture on Friday, February 19th, so there will be no new material that day, and you can use that day to work on the midterm. The last lecture which will be on the midterm is this lecture. The material for the lecture on Wednesday, February 17th will not be on the midterm. In terms of resources for preparing for the midterm, I guess there's 3 things I suggest. So the first thing is to use the practice exam and ensure you understand how to solve all the problems on the practice exam. The second resource would be to ensure you know how to solve all the problems on the homework. And the third resource would be to ensure you know how to solve all the problems in the lecture examples. So the best way to ensure you understand how to solve a problem is to explain the solution to someone else. You're never going to get as good a studying effect by copying out things on your own. It just doesn't work psychologically. If you want to really be confident you know how to solve a problem, you need to explain the solution to someone else. And so I suggest what you do is find people in the class group me to arrange study sessions where you take turns explaining solutions to each other without looking at my notes. And, the result of this explanation should be that the listeners feel they can also explain the same solution without looking at my notes. It's like explaining the solution to someone else and having that ability replicate itself is the test of understanding. The interactive lectures this Monday I'll design as preparation for the midterm. So if you want to come and think of questions that you might like to ask in preparation for the midterm. I encourage you to do that. As I said, I'll release the solutions to homework 3 and a practice exam and solutions to the practice exam at 9:30 on Monday, February 15th, and we can go through the practice exam problems during Monday's lecture. So, we can do it so that we try and have a collaborative effort where everyone, tries to participate in solving the practice exam problems, and I provide some sort of guarantee that this collective effort will succeed within a reasonable amount of time. Okay, so I guess that's everything I wanted to say about the midterm. All this information is in an announcement that I posted on Canvas. So in terms of today's lecture, this is probably the single most important lecture in the course because it introduces the main idea in mathematical probability, which is the concept of a random variable. So random variable is kind of, I don't get much intuition from that name. It's supposed to be a concept that expresses randomness, I guess, but if I were naming this concept, I would call it a measurement function. But it's called a random variable, and it's supposed to represent the concept of measuring the outcome of some experimental empirical phenomenon with real numbers. So you have this idea of a measurement function, and what it's supposed to do is associate a real number with each outcome in your sample space. So the way we want to think of it is that you're observing some kind of probabilistic or unknown phenomenon, and what you want to do is to quantify this somehow with a real number. So you're looking at something you don't understand, and you're getting some sort of experimental result that you want to work with. And a fundamental aspect of the scientific method is that if you want to study something scientifically, you should quantify it with mathematics. And what that ends up usually meaning is you want to quantify it either with integers or real numbers. And, obviously quantifying things with real numbers is more general than quantifying things with integers, because you can always assume that your real numbers are in particular integers. So random variables are a concept of quantifying experimental measurements. And, to anyone who has any clue of what STEM is about, it's obvious that quantifying experimental measurements is kind of what the whole intellectual chain from math to science to engineering to technology is about. It's about, numerical data and the ways that can be used to understand the world and then to build machines and provide services to people. And so, you know, in order to have the infinite power of theoretical math help you in understanding reality, you need to associate numbers to what you're seeing or hearing somehow. And that extremely primitive idea that, you know, we're just human beings in our bodies and we get various kinds of sense data from our eyes and ears and fingers, you know, we're taking literal sensory observations and quantifying them by assigning real numbers to what we see or hear. And that's the concept of a random variable. So, you know, the idea of probability is that the sample space is all the possible outcomes of something you're perceiving. And what the mathematics of probability that we've discussed under the axioms so far does is it allows you to talk about likelihood and answer the question, what is the probability of certain events? And then once we've done what we've done already in the course and discussed the probability of various events, then comes kind of the main intellectual leap in the mathematics of probability, which is to say that I'm going to go beyond just studying events described by properties, because events described by properties don't have enough numerical information for me to really generate a lot of useful insight by applying the power of theoretical math. So instead of just thinking about events defined by properties, I'm going to have a more quantitative data structure where on top of the things specified by the axioms of probability, I'm going to also have this measurement function which associates a real number to every outcome in my event. So, or every outcome in my sample space. And you can see I'm talking about two types of random variables, discrete and continuous random variables. So continuous random variable is just a word you can keep in your brain for later. We're not going to discuss that at all in this lecture or before the midterm. So we're going to talk about discrete random variables. So there's three equivalent formulations to defining a discrete random variable. And the most concrete one is what you can see on the bottom left, which is what I've just been calling a measurement function, which is something that takes every outcome in the sample space and returns a real number. And so what we're going to use for notation in that context is mostly capital letters like X, Y, and Z. So when you see a letter in particular capital X, that should make you think that this is a random variable. And, you know, like I said, I'm going to use the word measurement function to refer to what other people might describe as a concrete random variable, which is uh, just the definition of a random variable, but people use the word random variable in a kind of fluid way that can equivalently refer to any of the three definitions I have at the bottom of the page here. So we're going to think that, random variable is a term which is unfortunately ambiguous, and it has three equivalent definitions. The easiest definition to understand, the most concrete definition, is what we'll call a measurement function, and it's exactly what I've been describing, just a way of associating a real number to every outcome in the sample space. And so, to give you an example to keep in your head, the simplest of all probabilistic games is a game where you flip a fair coin and you get $1 if it's heads and you lose $1 if it's tails. So this is a game you can play forever, and theoretical mathematicians can tell you like a trillion digits of every single probability related to this game. You can ask any question about playing this game in the long term and we can answer that question, because mathematicians love extremely deep understanding of simple things, and this game is so simple that it's been played by human beings with rocks or whatever before anyone ever thought to invent dollars as a way of quantifying whatever thing of value you choose to barter in this game. But it's a game with two outcomes that are equally likely, and people wager equal amounts on opposite sides of the outcome, and that game is a random variable on the sample space consisting of heads or tails. From my point of view, it's a random variable where the value of x at heads is 1 and the value of x at tails is -1. So that's the measurement function for the simplest of all probabilistic games, based on the simplest of all probabilistic experiments, where you flip a fair coin, you get x of heads equals 1, x of tails equals -1, and both outcomes have equal probability. So the next most important way of describing a random variable is what we'll call a probability mass function. So a probability mass function is a list of numbers between 0 and 1 indexed by possible values of the random variable. So I'm going to use the letter V to refer to a value that the random variable can take. So in our simple game experiment, the two values would be V can be -1 or V can be 1. And then the definition highlighted in teal on the middle of the page at the very bottom is where you start to see the point of measurement functions, which is they give you ways to define events numerically. I have an event there in the right side of the middle teal equation where I'm talking about the probability of the event consisting of all outcomes where omega, where x of omega is v. So I'm looking at a value v and defining an event by taking what's called a level set of the random variable and basically asking, okay, what's the probability that my outcome solves the equation x of omega equals v? It's like you have now a mathematical procedure for defining probabilistic events, and that allows you to really start using some deeper ideas from theoretical math to understand the concept of chance and uncertainty that the whole subject is supposed to be about. So, this idea of a probability mass function is the basic way you use random variables to define events. Like, you pick a possible value of the random variable, you look at all the outcomes where the random variable evaluated at that outcome takes your particular value, and you ask what's the probability of that. And so we'll use that notation p subscript x of v, where v is the value and capital X is the random variable, which is referring to these three equivalent concepts, but most concretely denotes the measurement function, which is the kind of basis of the other two concepts. Then, in addition to the probability mass function, there's another really important way of defining a random variable, which is you can use what's called a cumulative distribution function. So the idea of the word mass in probability mass function is it's like you imagine all the outcomes like as different regions on a table. So for the you imagine all the outcomes, and then you think of the probability as a weight or mass that's placed on each outcome. So if you have like the probability mass function, it's like a mass placed on each outcome. And the cumulative distribution function is, instead of being indexed by possible values of the random variable, it's indexed by arbitrary real numbers, and you're asking what's the probability of the event that my random variable is no larger than t. So we have this notation f with a subscript of x, and then we're using t for an arbitrary real parameter, which you can think of as a bound on the probability. So the probability mass function tells us exactly what the probability is for each possible value. But the hard thing about that is you have to already know what the possible values you're supposed to look for are. The cumulative distribution function ends up being the easiest way to work with random variables mathematically, because it's just a function from numbers to numbers with no other restrictions on the inputs. So, you're asking, again, you're using this basic idea that I'm going to define events with my measurement function and ask what's the probability of the set of all outcomes where the the measurement function is no larger than t. And so that's what you get for the cumulative distribution function. Okay, so here's a more explicit analysis of the most elementary random variable, where you have this game as old as time of bartering equal amounts on two equally likely outcomes. So what we're going to say is that, okay, the measurement functions are the most concrete way of approaching random variables. So I'm going to think of $1 for winning heads, or winning $1 for heads and losing $1 for tails. So I'm going to write my sample space as two elements h and t, and then I'm going to have my measurement function from that sample space to the real numbers, which evaluates to 1 at heads and -1 at tails. So that's my measurement function, and like I said, measurement functions are in some way analogous to sample spaces in that they're very easy to understand on a theoretical level, but on a practical level it becomes difficult to work with them directly because you get overwhelmed with gigantic amounts of information. And the basic paradigm where the sample space is kind of a 2020's big data style arrangement with trillions of different points in it. It's really, working with a measurement function directly is just as bad as working with a sample space that's so large. It's like, if I'm Amazon and I have a sample space which is somehow representing all of my customers, and I need to deal with unknown and uncertain information on a sample space that's as large as Amazon's customer database, they have all kinds of random variables in that database. Like, one thing they definitely have is the total amount of money that person has given to Amazon in their history as a customer. So they have that random variable on this unbelievably complex and huge sample space. And, if someone at Amazon needs to make decisions based on information about total revenue from a customer, they can't just go through one by one and look at every single customer. So you need better mathematics to quantify and reduce the overwhelming complexity of information that comes from directly working with measurement functions. And that's where probability mass functions and even better cumulative distribution functions come in. Like, probability mass functions are kind of a intermediate step on the way from measurement functions to cumulative distribution functions. And the way this works is that cumulative distribution functions are functions from real numbers to real numbers with no restriction on the input, and theoretical mathematicians know a thing or two about such objects. And so we have all kinds of very sophisticated tools to apply to the study of cumulative distribution functions, and that's why most of the important theorems in probability are proved using cumulative distribution functions. But there's no question that measurement functions are easier to understand on a elementary level. So we can calculate the probability mass function for our simplest of all games and ask, what's the probability I measure a certain value? So that's what probability mass functions are designed to do. Like, if you look at the definition in the middle at the bottom in teal, it's saying, what's the probability I measure a value v? And the probability mass function answers that question. It tells you the probability you measure v is p sub x of v. Okay, so if we calculate how this works, we get px of 1 is the probability of the set of all outcomes, such that the set of all outcomes omega in heads or tails, such that x of omega equals 1. And that set is just heads, so it has probability 1/2. Often we'll abbreviate an event defined by a random variable by just writing the condition on the random variable that characterizes it and leaving out the extra set theory notation where we specify we're quantifying over all outcomes in the sample space. So you can see the notation I have in orange there, that the event being specified there, where we're looking at all outcomes in heads or tails where x of omega is 1, we may just abbreviate that as the event where x equals 1. And we can do the same calculation for -1. The event specified by x of omega equals -1 consists only of tails, so it has a probability of 1/2. And you can see the cumulative distribution function answers a similar question, but this question is a nicer question for mathematicians to work with because you can ask it for arbitrary real numbers t. Whereas the probability mass function question, you have to be able to make sure that you're asking it about a value of the function, because otherwise you're just going to get 0 and you're going to get no information. So like, unless you know what the values of the function measurement function are in advance, it's hard to work with the probability mass function on a theoretical level. But the question that's answered by a cumulative distribution function is very amenable to mathematical manipulation, because it's a question where you can ask the question for an arbitrary real number t, and you get a real number as an answer. So, you ask, what is the probability my measurement is at most t? And for our simple game, we're using the notation f of x of t for the cumulative distribution function. So, well, if t is less than -1, the probability is 0. There's 0 chance that I measure -386 as a result of this experiment. So anything less than -1 has 0 probability of exceeding the measurement. Then we can say, all right, let's look at the interval where -1 is less than or equal to t, and t is less than 1. In that interval, we have a probability of 1/2 of measuring something less than t, because the only probability that comes into play is the p sub x of -1. And then if 1 is less than t, we have that the probability of seeing a measurement less than t is 1. It's certain that the measurement is going to be less than t because t is bigger than 1, and the measurement can only come out to be 1 or 2. Okay, so the key theoretical information to understand about probability mass functions and cumulative distribution functions is written on this page. So the first thing you want to know is that I have a way of calculating the total sum of all the probability mass functions over outcomes, over the values, and it always comes out to be 1. So I'm using this notation range of x for a set of real numbers which consists of all the possible values of the function. And I have this sum over all possible values of the function where I'm adding up the probability mass function. And if you unpack the definitions, you can see that because different values define mutually exclusive events, this comes out to be a situation where you can turn a sum into a disjunction and get the disjunction of all of the... Oops, sorry, let me fix a typo here. Yeah, so you get the disjunction over all possible values of the event where the random variable is equal to that outcome. And so, or is equal to that value. So you are basically saying, what's the probability I get a value of 1 or I get a value of -1 in my simple game? And that probability is obviously 1 because if you take a disjunction over all of the events in the sample space, over all of the outcomes in the range of the event that the random variable is equal to that value, you get the whole sample space because we stipulated that the range exhausted all the possible values of the measurement function. So there's a specific formula for the sum over all possible values of the probability mass function. The formula is very simple. It's always 1. Okay. Then the cumulative distribution function, as I mentioned, is kind of the most mathematically substantial part of the theory of random variables, and it has some really nice mathematical properties. It's an increasing function. So the probability that the measurement is less than or equal to t is never larger than the probability that the measurement is less than or equal to t plus 1, or t plus a half, or t plus any positive number. So if I increase the upper bound on my measurement, the probability can only increase, and I see that I increase the value of f sub x, which is the probability of satisfying this upper bound on my measurement. We also want to observe that if we take the limit as the parameter goes to infinity, so if we, let's call this t so we don't get confused. If we have this parameter t in the cumulative distribution function, and we take some really large positive number, we have to see that this comes out to be 1, because as soon as t is bigger than every possible value, the probability is 1 because the relevant upper bound is satisfied by every value. And similarly, if we take like a number which is really close to minus infinity, like minus a quadrillion, the probability if all the values, if there's no values less than minus a quadrillion, the cumulative distribution function will be 0, because it's like, oh yeah, there's 0 probability of this because every possible value is greater than my upper bound I'm trying to put on them. And the way you actually calculate cumulative distribution functions is to go back to this idea that you can add up distinct values of the measurement function because they form mutually exclusive events and turn that into a disjunction. So the way you calculate the cumulative distribution function is to add up the probability mass function for all values of the measurement function that come out to be less than the upper bound you're putting on them. So the probability mass function tells you the likelihood of seeing every specific value. And in calculating the cumulative distribution function, what you're doing is adding up all of the probabilities for values less than or equal to your upper bound. Okay, so here we have an example. You can see this example has a long answer if we're going with my standard of highlighting the answer. It's a lot of numerical information that is asked for this question. So let's see what the question asks. It's a zero, there's no numbers, and it's a very short sentence. So how did I get so much numerical information out of this short sentence? It says, let X be the sum of the rolls of 2 fair dice. Determine the PMF and CDF of X. So PMF abbreviates probability mass function, and CDF abbreviates cumulative distribution function. And so we have this random variable defined by a measurement function on a 36 outcome sample space. We have 6 outcomes for the first die, 6 outcomes for the second die. We have 36 pairs of outcomes and a measurement function defined on that sample space by adding up the 2 numbers. And so you can see in the middle left, I have this 6 by 6 table where I've filled in the value of this measurement function at every pair of outcomes. So, you know, if you go to cell 1, 1, the sum of those is 2. If you go to cell 4, 3, the sum of those is 7. I don't even need to specify which order the rows and columns are because in this particular example, the sum is symmetrical and the kind of matrix I have there is symmetrical. But yeah, if you want to write out a measurement function, it ends up being a lot of numerical data. So now let's look at the probability mass function. So the range of this measurement function is the set of integers between 2 and 12. We can see from our table on the middle left that the takes every possible value between 2 and 12, and there's no values outside of those. So we know that what we have to do is we have to list out all the integers between 2 and 12 and calculate the probability that the measurement function is equal to that number. And the way we do that is by counting how many cells in the table there are at the middle left, which contain the number, and dividing by 36. So we have v equals 2, and p sub x of v equals 1 over 36, because there's one cell in the measurement function table with a 2 in it. And we can see if we look at v equals 9, there's is 1/9 because there's 4 cells in the measurement function table with a 9 in them, and 4 over 36 is 9. So that's how I filled out this probability mass function table, and we can do a sanity check, which is what mathematicians call looking at simple consequences or simple instantiations of your concept and seeing if they work out the way that they're supposed to. So we had this idea that is in the first bullet here about the probability mass function, that when you add it up over all values, the axiom of certainty tells you that needs to be 1. And so we can check that the sum of all these values is 1. I did not do that myself. I had an artificial intelligence do it for me, but it confirmed that this sum is 1. So it's very hard to get this thing wrong and still have them add up to 1. So, okay, now let's look at the cumulative distribution function. So what we want to do is we want to think that we're going to use the second of our main theoretical observations here, where you have a formula to calculate the cumulative distribution function in terms of the probability mass function by adding up all the probabilities less than or equal to that specific bound for values of the random variable in the range. So we can see what we have highlighted in the lengthy table at the bottom of the page. So there's these, well, I guess there's 12 columns in this table corresponding to these 12 intervals that are relevant to the definition of the cumulative distribution function for this random variable, because the cumulative distribution function only ever changes when you jump over a value which is in the range. And when you jump over a value which is in the range, the cumulative distribution function increases. So you can see if t is less than 2, its value is 0 because there's no values where the measurement function is, or there's no outcomes where the measurement function is less than 2. And then we say, okay, if t is greater than or equal to 2 and less than 3, then the cumulative distribution function is 1 over 36, because that's what I get by looking at the only value where the measurement function is less than t, which is 2. And another way of doing that would be to just count the number of cells where the measurement function is less than or equal to t and see that there's only one such cell, and I'm going to define or see that this is 1 over 36. And so if we look at the cell where it says 8 is less than or equal to t is less than 9, so how did I work that out? So what I can do is there's two approaches. I can look at the table I have for the probability mass function, and I can add up all of the values 2, 3, 4, 5, 6, 7, 8. So I got 13 over 18 by adding 1 over 36 plus 1 over 18 plus 1 over 12 plus 1 over 9 plus 5 over 36 plus 1 over 6 plus 5 over 36, because those are the values of the measurement function which come out to be less than this upper bound t, in the case that t is greater than or equal to 8 and less than 9. And so another way you could do that would be you could look at the various entries in the you could look at the various entries in the measurement function table. You could count that there's 26 entries which are less than or equal to t if t is between 8 and 9. And so 26 over 36 is 13 over 18. So that's how I calculated that, and I used the same ideas to calculate all of these other numbers. And you can try calculating some of these other numbers yourself if you want to check that you also understand these ideas. Okay, so I'll say again, this is the most important single lecture of the course because it's the introductory lecture to the most important topic in mathematical probability, which is the idea of a random variable quantifying some sort of empirical observation. And I'll also say that well, you know what I'll do? I'll put the practice exam on Canvas. I'll put the practice exam on Canvas now, and so you can look at it and see if you want to ask questions in Monday's lecture, and otherwise I encourage you to come to Monday's lecture with questions about things that might be on the midterm. Okay, so we'll end the lecture there.